On this worksheet, we're going to go through a few different types of problems that pertain to classifying matter. It's really just mostly about practicing different definitions that we use when we're classifying matter. The first problem, we're being asked to sort properties based on whether they are extensive or intensive. And in a nutshell, an extensive property is a property that depends on the sample size. So it depends on how much you have. Depends on the size of the sample, meaning that if you have more or less of a sample, that property is going to change. For example, the volume is an extensive property because if you have more of an object, its volume will be high, and if you have less, the volume will be lower. And the same with mass. Mass is also an extensive property. Obviously, if you have more of something, it will be heavier. Intensive properties are things that don't change with the size of the sample. So for example, water has a melting point. I'm going to abbreviate that MP, that's a standard abbreviation. Water has a melting point of 0 degrees Celsius, and it doesn't matter how much water you have, the melting point is always 0 degrees Celsius. Also, the color of an object is an intensive property. Now, the depth of the color, like the darkness of the color might change, but the color itself, is it red, is it green, whatever, that's not going to change with sample size. Flammability is also intensive. Again, like the severity of the flammability will depend on how much you have. If you have a tiny bit of gasoline versus a huge amount of gasoline, fire is going to be definitely bigger, but flammable, it's all flammable. Conductivity is intensive, meaning that it doesn't matter how much you have, it's going to be either conductivity or not conductive. The smell, the odor, this is another one that if you have a lot of an object, if you have a small sample size versus a large sample size, the odor is going to be more intense if you have a large sample size. But whether or not an object has an odor it does not depend on the size of the sample. The pH of an object is independent of sample as well, so that's intensive. And then last but not least, density. Density is one that does confuse a little bit of students because they think density, as you know, is the mass over the volume. And mass and volume are both extensive. If you have a large sample, that means you're going to have a large volume and a large mass. So they think density must be extensive as well because density involves mass and volume. But remember, density is the ratio of mass or volume. So if you have a small sample size, the mass will be small and the volume will be small. If you have a large sample size, the mass will be big and the volume will be big. And so because of this ratio, this relationship, density ends up being intensive. For the next problem, we're just going to be drawing pictures of water as it is going from a liquid to a solid. And so what we're looking for here, I'm going to use just a single sphere to represent the water molecule. What we're looking for here is when water is a solid, it is going to take the shape of its container and it's going to be pretty orderly in this sample. So that means we want to draw these little water molecules relatively kind of lined up with each other. And there's some sort of pattern with these molecules. So I'm kind of stacking them like this in the little kind of empty spaces. When a substance is a liquid, the molecules are still in contact with each other, like I've drawn here, but they don't have an order to them. So I'm going to try to draw these water molecules a little bit more random than the ones in the solid. And that is kind of presenting a challenge because I'm, first of all, not a very good artist. And second of all, it's kind of hard to do this when you have spheres. But what I'm attempting to draw here is that it's not as orderly as it is when it's a solid. When it's a solid, we have this nice order to it, and as a liquid, it's just more disordered. Does this represent a physical change or a chemical change? A physical change is when we are just changing from a solid to a liquid, or from a liquid to a gas, or vice versa, any of those, vice versa. Changing whether or not it's what its state is. So this would be a physical change because we are changing from liquid water to solid water. A chemical change is where you change an object's identity, change what it is. So a chemical change would involve changing this into something that's not even water anymore. change what it actually is, may or may not include a change to the state as well. So maybe it's also changing, that's not how you spell change. Maybe we're also changing from a solid to a liquid to a gas or vice versa, but it's not necessary. In a chemical change, you could be changing from a liquid to another liquid. The big thing with the chemical change is that you start with one type of molecule and you turn it into something completely different. Here's another pretty similar problem. This is telling us we have this liquid water and we're converting it into hydrogen gas and oxygen gas. I'm going to try to make my drawing a little bit better this time. So I'm going to use, for this, I'm going to use red circle and blue circles to represent my water molecule. The blue circles are the hydrogen atoms, and the red circle is the oxygen. And I'm going to use this technology to just sort of put a whole bunch of water molecules in here. Well, 4, we'll say. And what I'm going to do, because this is supposed to be a liquid, I am going to just sort of move them around kind of randomly. Remember that we want them to be sort of not in any particular order because it's a liquid. If it's a solid, they're in some sort of nice arrangement or some sort of nice pattern. They're kind of disordered. I'm going to maybe make them a little bit bigger so that they fill up the space here. And so over here in the second box we want to draw, it says hydrogen gas and oxygen gas. So for this, I'm going to draw the hydrogen gas as 2 blue spheres together, and the oxygen gas is going to be 2 red spheres together. And these are gases, which first of all means we don't want to have them settling in the bottom of the box. We want them all over inside this container, and they're going to be not touching each other. So we don't want to have them in close contact like this. So that's going to look something like a couple of hydrogen gases. I'm not going to be getting the quantity correct. I'm just going to draw a few in there. Here's a couple of oxygen gases. So I just want to have them sort of spread out, not touching each other, filling up the whole entire container. Does this represent a physical or a chemical change? Let's look back at those definitions. A physical change is where we're just moving from a solid to a liquid to a gas. A chemical change is when we're changing what the object actually is. We're starting with water and we're turning it into something that is not water. It does have the same components, hydrogen and oxygen, but it's not water anymore. So that makes this a chemical change. And we're also doing a change in state. We're starting as a liquid and ending as a gas, but again, that's not a requirement. The last problem that we have on here is to classify these substances based on whether they are homogeneous or heterogeneous mixtures or pure substances. I'm going to start with the pure substances. Pure substances are going to be things that are on the periodic table, which is why I have one handy. That's not the only definition, but we're just going to start with that right there, first criteria. So if you have something and you can find it on the periodic table, that means that you're looking at a pure substance. This is typically going to be things that are represented by their atomic symbol. Atomic symbol is a 1 or 2 letter symbol. The first letter would be capitalized, the second letter would be lowercase. And so there are 2 of those on here. We have gold, which is AU, is right here on the periodic table. And then mercury also. So I'm going to cross those off. So these are examples of types of atoms, and all of the different types of atoms are on the periodic table. Another thing that is going to be a pure substance is going to be something that is represented by a molecular formula. I'm just going to call that a molec form. A molecular formula is going to be this same type of notation, letters, but more than one element put together. So this one is 2 elements, a hydrogen and a chlorine. And anything that is represented by a molecular formula is also going to be a pure substance. This is another type of a molecular formula. So that little 2 is letting us know that we have 2 oxygen atoms like that. So there's that. And there's another one, O3, and we have another one, H2O, and another one, H2O2. So those are all pretty easy to figure out. Now, everything that's being represented by words, these things are probably mixtures, but they might be pure substances. We do want to look out a little bit because maybe somebody would just use the name of the element, like copper. They might just say copper. And if they just use the word copper instead of writing the symbol, that would be an example of a pure substance. It's just being represented by its name instead of being represented by its symbol. None of the things that are on this list are pure substances, or none of the things that are left, I should say, are pure substances. They're all mixtures. So homogeneous versus heterogeneous mixtures, what are the differences between the two of them? It really has to do with what we see when we look at it with our eyes, not under a microscope, but just with our eyes. Focusing on the prefixes homo versus hetero. Homo is the prefix that means the same, and hetero is the prefix that means different. In a homogeneous mixture, the components of the mixture look the same. They have the same appearance. So when you look at the mixture, you don't see the individual components. In a heterogeneous mixture, the components all look, or at least some of the components look different from each other. So when you look at the mixture, you can see the different components. And a good example of that would be trail mix. When you look at trail mix, you can see the peanuts, you can see the raisins, you can see whatever is in there. Or pizza, that's also a good example of a heterogeneous mixture because you can see the pepperoni and you can see the cheese. Air is usually a homogeneous mixture. When you look at air, you don't see the oxygen versus the nitrogen versus the pollution. Normally, sometimes when things are really bad, air could be a heterogeneous mixture, but normally it's homogeneous. Also, same thing with tap water. Tap water has, the water molecule in it, but it also has a lot of minerals depending on where you live, like magnesium or iron, things like that. And normally, when you look at tap water, you can't see all of the components in your tap water. Sometimes you can. Brass, if you're not familiar with brass is the metal that's used to make a lot of musical instruments like saxophones, trumpets, things like that. It's that kind of gold-colored metal. When you look at brass, you don't see the individual components. It just all looks the same. Pepsi that's not flat is a heterogeneous mixture because when you look at it, you can see those little bubbles of carbonation. So you're seeing one of the components, the carbonation. But flat Pepsi, flat means that it's lost its carbonation. When you look at that, you don't see the bubbles. It all looks the same. Nothing stands out to you. Salt water is kind of a tricky one to classify. I'm going to call it a heterogeneous mixture because usually when you're looking at, I don't know. I don't really know where to put it. It really depends on the source of the salt water. I'm going to kind of set it in the middle. Salt water, if you're just like taking a glass in your kitchen and putting some water in there and then sprinkling some salt in it, that's probably going to be a homogeneous mixture. Maybe I'll decide that it belongs over here. But if you had like water from the ocean, like we'll say seawater, there's usually a lot of stuff floating around in there that you can see with your eyes. So that would be a heterogeneous mixture. But sometimes with some of these, like with the salt water, it really depends on the actual sample itself. And same with air and same with tap water. We could say that most of the time air is homogeneous, but we can all think of circumstances where it's actually a heterogeneous mixture. So, it's just sort of depends on the circumstances.